Alrighty, so here we are with Chapter 10, Section 5, notes, and we are talking about the effects of changing dimensions proportionally. So our objectives today are to describe the effect on perimeter and area when one or more of the dimensions, like length or width or height, of a figure are changed, and for 2, to apply the relationship between perimeter and area in problem solving. So the idea here is that if you have a change in dimensions, meaning a length, a width, or a height, or a perimeter, or a circumference, or whatever it happens to be, is multiplied by a number in one dimensions, that means that all of those things are changed by that factor of a that you multiplied by. So again, one-dimensionally, if you multiply any of the lengths, you're going to then increase your perimeter or your circumference by that same factor. So for example, if you had a length of a side of a square of 2, but then you doubled all of those lengths, your perimeter would double as well. All right. So then in 2 dimensions, talking about area, okay, if you have a change by all of your lengths, for instance, of that square I was just talking about, by a factor of a, the area that would have been 4 to begin with changes by a factor of 2 squared. So 4 so your area is now 16. So again, in 2 dimensions, if you're talking about what happened in 1 dimension, you're going to square what happened in order to get that new idea. All right, so we'll go ahead and try some of these. So the first one here, example, is to describe the effect of the change on the area of the parallelogram. So we're talking about area if the height is doubled. So again, something's happening here being multiplied by a 2 for doubled, okay? But then what happens to the area? And so we can predict that if this number is 2, then the area is going to be multiplied by 2 squared. But we will show the work for how that works. So the original dimensions of the area of this parallelogram are going to come from a half, the first base plus the second base. Oh, sorry, this is a parallelogram, so just base times height, sorry. I thought it was a trapezoid for a second. All right, so the area is the base times the height. And notice that the base is 12 meters, and then the height between them at 90 degrees is 9. So that means that our area is a base of 12 and a height of 9. And so we have an area of 108. All right, and so that's the area, again, with just the original dimensions. But now we're going to double all of them. So instead of having a base of 12, our new base is going to be a base of, oh, it just says the height. So the base stays the same. The height is going to be, instead of 9, we're going to multiply it by 2 because it's doubled. So now it's 18. All right. So when we find our area, we're going to use the same area formula, but of course now our new base is, well, our same base is 12, but our new height is 18. So our total area is 216. So if you take a look at 108 and 216, in order to get from one to the other, you multiply by 2. Or double. So if you double one of the lengths, you double the area. So we'll write that here. Oops. And apparently I spelled double as double, but anyway, you get the idea. All right. So the next piece, a triangle has vertices of A11, so we should plot that. a B61, and C35. So we have our triangle here. And we need to describe the effect of the change on the area of the triangle when the base and the length, or the base length, is multiplied by a half. All right. So we're going to do the original dimensions. So the area of our triangle originally is going to be a half base times height. The base of the original triangle has a base of 1, 2, 3, 4, 5. And the height of the original triangle has 1, 2, 3, 4. And so our area is a half times 5 times 4, or 10. So the area of this triangle is 10 units. You'd fit 10 squares inside of there. All right, but then if we try the next one, which was multiplying the base length by a half, so now we're kind of shrinking it. Looks like it's going to have the same, what was the base length? 5. So it's going to have like a 2.5 length there. And so we're actually talking about this triangle. Because notice it has the same height, but it has a base length of half of the previous one, or multiplied by a half the fraction. So area is still going to be a half base times height, but in this one, our base is now 2.5, and our height is still 4. So as we had previously, if we doubled the length up here, we doubled the area, and over here we're halving the length, so we're going to probably take a half of the area. So your area is a half times the base, which was 2.5, times 4. And so that means that we're going to have 5 for our area. So noticing the relationship between 5 and 10, we multiplied by a half. And so our conclusion is, if you half one length, you half the area. All right, so that is proven. Sweet. So the next one here is talking about effects of changing dimensions proportionally, meaning not just one dimension, but all of them. So in this case, we're describing the effect on the perimeter and the area of a rectangle with base of 8 and height of 3 when the base and the height are multiplied by 5. So the official start of our image here is talking about a base of 8 and a height of 3. But then when your dimensions are multiplied by 5, the next rectangle, which is not drawn proportionally, is going to be 40 meters by 15 meters. And so we're going to talk about what happens to the perimeter and the area when you do this. So the perimeter of this first shape here is supposed to be 2 bases and 2 heights. And since our base is 8 and our height is 3, we have 2 times 8 plus 2 times 3, or 16 plus 6, which is 22. So your perimeter is 22 of the original one. If we're looking for area, of course, area of a rectangle is base times height, and so we're just looking at 8 times 3, or 24. So this is the original area and perimeter. The next one talks about perimeter, which is still 2 base and 2 height, but now our base is 40 and our height is 15. And so we'll have 80 plus 30, and so 110. The next one is our area, and the area is base times height. And our base is 40 and our height is 15. And so 40 times 15 leaves us with 600. All right. So what we need to do to talk about the perimeter is figure out what is the difference between 22 and 110. So to get from 22 to 110, (110) divided by 22 is 5. So what we end up doing to get from one to the next is multiply by 5. All right, and that kind of goes with what we were talking about here. We said if we have one dimension and we multiplied a dimension or all dimensions by a, it changes by a factor of a. So it doesn't necessarily change what's happening there. So we took our perimeter and multiplied by 5 from the original perimeter because we made all of the side lengths by 5 bigger. That meant that anytime you want to take the perimeter and get it from the previous one, you just multiply by 5. So perimeter was times 5. The next one is your area. And so the area idea was that we had 24, and then we moved via some operation to 600. And so you need to find out how do you get from 24 to 600. So really we would just divide them. And so 600 divided by 24 is 25. And so technically we are multiplying by 25. But remember that 25 actually came from 5 squared. And so hopefully we can see that this 5 is still part of it. So notice this one said multiply by 5. This one also says multiply by 5, but 5 twice. So 5 times 5. All right. So again, our description is the perimeter needs to multiply by 5 to get the new perimeter. The area, if you change those dimensions, needs to multiply by 25 to get the new dimension. All right. Then our next one, we're describing the effect on the circumference, which is still like a perimeter. So we are going to get these same results, only now we are multiplying by a third. So now this is going to change to a third, and this will change to a third squared, which is a ninth. So we'll talk about that in a second. So circumference is 2 pi r. And in the problem here, our radius is 9 inches. So we're going to take 2 times pi times the radius of 9. And so we get 56.5487. We have to be careful of that because if we keep it like this, we might not see the change. And so I'm going to also just write 18 pi because those two are equal. Okay. So we'll kind of mention that. All right. Then the next one is going to be the area. And so the area of this coming from a radius of 9 is pi r squared. And we have a radius of 9, so pi 9 squared, which again could be your decimal of 254. Whoops, that's not a 5. 254.4690 or 81 pi. But again, those are the same. Then if we move on to changing the dimensions, so now our new radius is going to be 9 divided by 3, which is 3. Okay. So our new perimeter, or sorry, circumference, which is technically the perimeter, circumference is 2 pi r, but our radius is now 3. And so 2 times pi times 3 makes 18.8496, Or again, since we don't necessarily want to see that decimal, so we can actually see the difference here, we'll write it as 6 pi. And then the second piece wants you to find the area with that new radius, which is 3. So we'll have pi r squared or pi 3 squared. And so pi 3 squared is 28.2743, but again, easier to see it if it was just written as 9 pi when we look at our differences here. All right, so looking at the circumference, to get from 18 pi to the new circumference of 6 pi, from 18 to 6, you're going to divide by 3. But of course, dividing by 3 is the same as multiplying by a third. And so we're going to say we multiplied by a third, which is again what the problem indicated that we would do anyway. However, jumping from circumference to area, area is moving from 81 pi to 9 pi. And so that's not multiplying by a third anymore. It's actually multiplying by a ninth. And so how do we get 1/9? We realize that 1/3 squared is 1/9. All right, and so remember that anytime that you're changing a dimension, proportionally in this case, so for every single one of the dimensions, in this case there is only one dimension anyway of a radius, you're going to multiply by that same number if it's circumference, but for area you're going to multiply by that number squared. All right. So here's our next piece here, which is just effects of changing area. So now instead of going from the dimension to the area, we're going to go from the area back to those lengths. So a square has a side length of 5 centimeters. If the area is tripled, what happens to the side lengths? All right. So a square has a side length of 5 centimeters. And so if we think about the area of a square, that's going to be your side length squared or 5 squared. So the original is 25. The tripled area is going to be 3 times 25, which is going to be 75. So to get from 25 to 70, to get from 75 back to the side lengths, so again, area, what happened to the side length, we're just asking ourselves what times itself makes 75. All right. And so, of course, technically, what number times itself making 75 is actually taking the square root of it, because we're asking 75 is supposed to equal some number squared. And so how do we undo a square? We'd take the square root. And so we'd end up with a side length of the square root of 75. But of course, that as a decimal is probably a little easier to look at. So 8.6603 is your new side length. All right, and so taking a look at tripling the area, okay, so multiplying by 3, what's going to happen with the side length is that it's going to move from 5 centimeters to 8 centimeters. Or 8.6603 centimeters. And so in order to get from 5 to 8.6603, you end up multiplying by 1.73. And so when you multiply by 1.7321, again, your calculator won't necessarily tell you this because it's an irrational number. It's actually the square root of 3. And hopefully that makes sense, because if we are multiplying by 3 for an area, we want to get backwards. And what's the opposite of squaring? Square rooting. All right. So then the last example is that a circle has a radius of 6 inches. And so if the area is doubled, what happened to that circumference? And so remember that circumference is a length. And so if the area is multiplied by 2, remember to go back to the length, we're probably going to multiply by the square root of 2. Just like in our previous example, when we multiplied by 3, technically the length multiplied by square root of 3. All right, so we'll go ahead and actually find these dimensions just to double check. So the original dimensions have an area of pi r squared, or pi 6 squared, or 36 pi. Their circumference is going to be 2 pi r, or 2 times pi times 6, or 12 pi. For that doubled area, our new radius is going to be 12. Oh, sorry, not our area. Our area is doubled. And so our new area is going to be double of 36 pi, which is 72 pi. All right. And so in order to get backwards from an area of 72 pi to the radius, we can go ahead and set that equal to pi r squared divide both sides by pi, and we get a radius squared that's 72. Take the square root of both sides, and we get a new radius of the square root of 72. The square root of 72 is actually 8.4853. And so that's our area. To get back to the circumference, we would plug in this as our new radius. And evaluate. And so we're left with 16.9706 pi. And so now we're trying to find out, how do you get from 12 pi to 16.9076 pi? So 16.9706 divided by 12 has you multiplying by 1.4142. But of course that is equal to the square root of 2. So we're technically multiplying by the square root of 2. All right, and again, the way that I found this was that if the area was said to be doubled, then a distance, or a length, which is circumference, would be the square root of whatever was asked. All right. To kind of put this into perspective, the idea is that you have one dimension, okay, and things that are in your one dimension are your lengths, like your base and height and radius, and other lengths like your distance or circumference. And then you have two dimensions, which is your area. Okay, and so the idea is that if you ever do something to get to your two dimensions, so let's say that we multiply by x in order to get backwards, you're going to have to multiply by the square root of x. All right, so again, to get from here to here, we're multiplying by, x squared to move from 1 dimensions to 2 dimensions. But to move backwards from 2 dimensions to 1 dimension, you'd end up multiplying by the square root of whatever that x factor was. And again, x is your operation of change. So again, I usually think of this diagram. To get to here, you squared it. To get back here, you square root. All right. These are our notes from 10.5, and so we should be able to do the assignment.